Hi, my name is Anshu and welcome to my channel Bottleneck. This is a Scala design pattern series. In this video, we are going to discuss about Scala specific type class design pattern. Alright, if you are not able to follow along on any of these concepts, then hold on tight. We will discuss each of these concepts in detail with examples in the follow-up sessions or videos. So, the type class design pattern, which is closely related to implicit design pattern, as we are going to leverage lot of things from the implicit design pattern. Alright, if you have missed on to my previous video on implicit design pattern, then I will post the link in the description. So what is a type class design pattern? A type class is a trait that takes a type and describes what operations can be applied to that type. A type class in Scala allows you to add behavior to types without modifying their source code, which is also known as pimp my library. It enables ad hoc polymorphism and a type checking. So in normal class, as describes a collection of methods and properties, something must have in order to belong to that specific type. The type checker for compiler can use this information at compile time to find errors in the source code. This process is well known as type checking. Now, in a type class, as opposed to a normal class, lifts this same concept to a higher level. So it lifts the type checking to a different level, applying it to types. So it describes a collection of properties on methods that a type must have in order to belong to that specific types. We can break down the type class into multiple steps. Like first one would be the defining a type class, which is nothing but a trait which takes a type parameter and just defines some operations on top of it. Now the second is creating instance or a class instance of the those operations for a specific type, and implementations can be implicit or explicit. Now once we have done the instantiation, now we have two way out. The first is surface out the type class instance by creating a companion object and writing an apply method, which will allow us to use a type class without knowing that it is there. That is first. Second is pimp my library, where we are going to create implicit class on top of that type with a given defined couple of methods. So it will look like that it's a built-in methods when we are going to use that type. All right. So what is ad hoc polymorphism? Ad hoc polymorphism in Scala often refers to as a type class based polymorphism, in a form of polymorphism where functions or a method can operate on a different type and appropriate implementation is selected on the type of arguments provided. This is different from the other forms of polymorphism. So if the behavior is based on the specific type, provided the implementation is selected based on the type at compile time, typically using implicit resolutions. All right. Now type safety. So it ensures the correct type. The Scala type system ensures that the operations defined in a type class can only be used with the type class that have the instance of the same type class. So it cannot be two objects of different type class cannot be same. So that we can induce, that can be done, as well as that will be checked at the compile time. So it has a compile time check that for the correct type instance when you are comparing the values. Now implicits. So we had implemented a lot of implicits in our implicit design pattern series. I will post the link in the description. Now what is magnet design pattern? Magnet design pattern in Scala is a design pattern that leverages type classes and implicit conversions to achieve flexible and type safe method overloading. It addresses two specific problems. One is the method overloading, another is the problem with super. So that we are going to see in action when we are going to implement. All right. Now the next thing is variance. So variance is a problem of inheritance, a type substitution basically. Now variance refers to as subtyping between complex types like the generic type, and relates to subtyping between their component types. There are three kind of variances, which is invariance, covariant, and contravariance. Describes different ways in which subtyping relationship of parameterized types can reflect the subtyping relationship of their parameter type. So we have type and their parameters. So we have to keep in mind, and all of these three revolves around them. So what happens with invariant? A type parameter in invariant, if the parameterized type has no relationship to other parameterized type based on the type argument. So if there is no inheritance defined, in this case, the type class in Scala are typically invariant. Invariant is the default in Scala and is used when the operations of the type class or the data structures do not naturally support covariant or contravariance. This is often the case when the type parameter appears in both input and the return position within the method. So if it has A and A both sides, it is going to be an intravariant that we are going to see as an example. So similarly for covariant, it is a parameter's type, it's a subtype where the type parameter is a subtype as well as, so for a given parameterized type, if we have a subtype and a supertype convention, so covariance is typically used when type with used in type classes where the type parameters only appear in the return type. Now example would be a functor. So if we, okay, so we will deal with the examples when we are actually implementing this. So type class that transforms a value inside a container, the transformation does not depend on the specific subtype. So you can think of map or a flat map as an example for covariant. For contravariant, a type parameter is contravariant if the parameterized type is a supertype when the parameter type is subtype. So the contravariance is useful in type classes where the type parameters only appear in the input. So once the output is transformed, we are going to use this contravariant approach. All right. So now we have bounds, that is context bound. So in Scala, context bounds, upper bounds and lower bounds are concepts related to type parameter that restricts the type that can be used as an argument for a generic method or classes. A context bound is a constraint on a type parameter that requires an implicit value. It can be explicit as well for a specific type, often a type class instance, to be in the scope. So context bound directly relates to the type classes as we see, and they enforce that our type class instance is available for the type parameter, ensuring the type conforms to the behavior defined by the type classes. So that ensures the type class instance, whether implicit or explicit, is available for the type parameters. So now the lower bound, less commonly tied to the type classes but relevant when using that a parameter can accept supertypes, often in the scenario involving variance. Now it restricts a type parameter to be a supertype of a specified type. Upper bound, similarly, useful when you need to restrict a type parameter to types that inherits from a certain trait or classes which can be combined with types, and the type itself has an inheritance relationship. So it restricts basically type parameter to be a subtype of a specified type. So as this lower bound, it is clearly visible, so it is a subtyping and this is super typing. So we will see them in example once we implement. Now the pros and cons, as we see, the more or less it is extensible because we are enriching the type. It is type safety because we are enabling it for the compile time check, and it makes code more flexible. So once we deal about the method overloading or lifting, then we will see how it makes how it makes code more flexible. But there are some cons like hidden behavior. So we will be using implicits. If not used carefully, this will overcomplicate things. That there will be some boilerplate code which will eventually, uh, while creating type classes, we need to write couple of lines of code which will be eventually boilerplate code. Always there is an alternative to write it in a plain imperative style, but if you use type class, you will see the difference how we can improvise on the given scenarios. And of course, complex debugging. If we involve all of these concepts of implicits and type classes, the debugging process will become nasty. All right. So that is all about the type class design. and we will discuss all of them in detail with implementations. If you enjoyed this video, please like and subscribe, and see you in the next video. So we will have follow-up videos, multiple videos to understand all of these in detail. All right. Thank you.